Imagine waking up tomorrow morning to an unusual situation. The United States calls an emergency meeting. China does the same. European governments quietly pull their top officials into closed rooms. There's no war, no market crash, no pandemic. Just one private company making a decision. And suddenly factories stop. Military projects are delayed. AI research slows down. Electric car production lines fall silent. This isn't science fiction. This is how the modern global economy actually works. And at the center of it all is a single company, based in a quiet town in the Netherlands. Most people have never heard of it. But without it, the modern world as we know it simply cannot exist. That company is called ASML. And quietly, without flashy products, celebrity CEOs, or social media hype, it has become one of the most powerful choke points in human history. ASML doesn't make phones. It doesn't design software. It doesn't sell weapons. ASML builds a machine. Just one type of machine. But this machine is so complex, so precise, and so difficult to replicate that no country on Earth can build it on its own. And without this machine, advanced computer chips become impossible to manufacture. Smartphones, artificial intelligence, electric vehicles, satellite systems, military hardware, supercomputers, all of it depends on this single technology. And ASML is the only company in the world that controls it. Normally, when something is this important, it's owned by governments, or at least produced by multiple competing firms. ASML is neither. It's a private company, and it has no true competitor. Which means if ASML decides not to sell its machines to a country, that country, no matter how rich or powerful, falls years behind in technology. This isn't hypothetical. It's already happening. But to understand how we got here, we need to rewind. This story doesn't begin with AI, or smartphones, or geopolitics. It begins with a simple scientific problem. For decades, the tech industry followed a basic rule. Smaller transistors make faster computers. This idea became known as Moore's Law. Every few years, chips got smaller, faster, and more efficient. But eventually, engineers ran into a wall. Light itself. Traditional manufacturing uses light to print circuits onto silicon. But visible light simply isn't precise enough to draw features at the atomic scale. If you want to build transistors just a few nanometers wide, you need much shorter wavelengths of light. And that's where everything changes. This is where extreme ultraviolet lithography comes in. UV. On paper, it sounds simple. In reality, it is arguably the most complex machine humans have ever built. UV light doesn't exist naturally. It has to be created artificially. To do that, molten droplets of tin are fired into a vacuum. Each droplet is hit by an incredibly powerful laser twice. The impact turns the tin into plasma, hotter than the surface of the sun. That plasma emits extreme ultraviolet light. Then comes the hard part. That light cannot be focused using normal lenses. It has to be reflected using mirrors. Not glass mirrors. Perfectly layered metal mirrors. Mirrors so smooth that if a single atom is out of place, the entire system fails. All of this happens in a near-perfect vacuum. No air. No dust. No vibration. An EUV machine contains over 100,000 components. It's more complex than a jet engine, more precise than any medical device, and more fragile than almost any industrial system ever created. When ASML ships one of these machines, it doesn't arrive in a box. It arrives in pieces, loaded onto dozens of cargo planes, installed over several months, calibrated for weeks. And when it finally works, it enables something extraordinary. The most advanced chips on Earth. At this point, the obvious question is, why can't other countries just build their own version? The United States has world-class engineers. China has unlimited manufacturing scale. Europe has deep scientific expertise. But EUV lithography isn't just one breakthrough. It's the result of decades of failed experiments, government funding, supplier coordination, and institutional patience. Thousands of specialized suppliers, some making mirrors, some making lasers, some making software, none of them replaceable. ASML didn't plan to dominate this space. In fact, for years, many experts believed EUV would never work at all. But ASML kept going. Governments funded it. Partners stuck with it. Competitors gave up. And eventually, ASML crossed a point of no return. Today, it is the final gatekeeper. Without ASML, the global semiconductor supply chain is incomplete. The United States designs the best chips. Taiwan manufactures them. Japan supplies materials. Germany supplies precision tools. But EUV lithography? That only comes from one place. And as chips stopped being just consumer products and started powering AI systems, military hardware, and national infrastructure, ASML became a geopolitical issue. The United States began applying pressure. Advanced machines could no longer be shipped to China. Licenses were delayed. Exports were blocked. ASML was caught in the middle. On one side, its biggest future market. On the other, U.S. national security interests. And this is where the story stops being about technology and starts being about power. Because when a private company sits at the center of global progress, every decision it makes carries consequences far beyond profits. If ASML miscalculates, supply chains don't just suffer. The global balance of power shifts. And this brings us to the real question. Not whether ASML is powerful, but what happens if this system breaks. Because the more advanced technology becomes, the more fragile this entire structure grows. And in the next part, we'll see how one quiet company became something no government can afford to lose control of. What makes ASML truly dangerous isn't just its technology. It's the position it occupies. In the modern world, power doesn't always come from armies or oil fields. It comes from control over bottlenecks. And ASML sits on one of the narrowest bottlenecks ever created. To understand why governments are so nervous, we need to zoom out and look at how fragile the semiconductor ecosystem actually is. A modern chip is not made in one country. It isn't even made by one company. It's the result of a global relay race. Design often starts in the United States. Manufacturing happens in Taiwan or South Korea. Materials come from Japan. Precision components come from Germany. Each step depends on the previous one. And if even one link breaks, the entire chain collapses. For years, this system worked because no single player controlled everything. Until EUV. EUV changed the balance because it created a single point of failure. Every advanced chip below a certain size requires EUV lithography. And every EUV machine comes from ASML. There is no backup supplier. No alternative technology waiting in the wings. Which means governments can't simply diversify risk. They can't stockpile EUV machines like oil reserves. They can't build them domestically in a few years. The learning curve is too steep. The supplier ecosystem is too specific. The institutional knowledge is too deep. And this is where geopolitics enters the picture. For decades, technology flowed relatively freely across borders. Companies sold to whoever could pay. But as chips became central to artificial intelligence and military systems, that openness disappeared. Suddenly, advanced chips weren't just economic assets. They were strategic weapons. The United States realized this first. If advanced chips power AI and AI powers surveillance, drones, cyber warfare, and autonomous weapons, then chip supply chains are no longer neutral. They're matters of national security. So instead of targeting chip designers or manufacturers directly, the U.S. focused on the chokepoints. And the narrowest choke point of all was ASML. Pressure began quietly. Diplomatic conversations. Export licenses delayed. Regulatory reviews. Eventually, the message became clear. Advanced EUV machines should not reach China. Not because ASML wanted this. Not because the Netherlands demanded it. But because the United States understood something crucial. You don't need to control the whole system. You just need to control the narrowest gate. For ASML, this created an impossible situation. China represents one of the largest semiconductor markets in the world. Blocking sales means walking away from billions in revenue. At the same time, ASML depends heavily on U.S. technology and suppliers. Its lasers, software, and components are deeply intertwined with American firms. Defying U.S. pressure wasn't really an option. So ASML complied. And with that decision, something unprecedented happened. A private European company became a frontline asset in a global technological Cold War. China felt the impact immediately. Despite massive investment, despite thousands of engineers, despite government support, Chinese chipmakers hit a wall. They could manufacture older chips. They could improve yields. They could scale production. But without EUV, they couldn't move forward. This wasn't about money. It wasn't about effort. It was about physics, time, and accumulated expertise. And that's what terrifies governments. Because this kind of power can't be easily transferred, regulated, or replaced. ASML doesn't answer to voters. It doesn't operate under military command. Its incentives are commercial. Its decision-making is corporate. Yet its impact is geopolitical. What happens if ASML continues to dominate? What happens if the technology hits a wall? And what this story tells us about the future of globalization itself. As we look forward, the most important question isn't whether ASML will remain powerful. It's whether this model of global dependency is sustainable. Because EUV lithography may not be the end of the story. ASML is already working on its next generation of machines. Systems even more complex, more expensive, and more difficult to replicate. Each new generation pushes closer to the physical limits of matter. Atoms don't like being controlled at this scale. Heat becomes unpredictable. Errors multiply. Progress slows. And when progress slows, stakes rise. Governments understand this. That's why we're seeing massive investments in chip sovereignty. The United States is reshoring manufacturing. Europe is subsidizing fabs. China is accelerating domestic alternatives. But none of these efforts remove the central problem. They all still depend on ASML. You can build a factory anywhere in the world. You can train engineers. You can subsidize production. But without EUV, the factory is incomplete. This creates a strange future. A world that looks multipolar on the surface, but remains unipolar underneath. Many countries, many flags, many strategies, one technological gate, and gates create tension. If ASML sells to everyone, it risks enabling rivals. If it withholds technology, it risks fragmenting the global economy. Either choice carries consequences, and neutrality becomes harder with each passing year. At some point, ASML may be forced to choose, not between customers but between systems. A world of open trade, or a world of technological blocks. This wouldn't just reshape the chip industry. It would reshape globalization itself. Because semiconductors are no longer just inputs. They are the foundation of modern life. Transportation, energy, communication, defense, healthcare. All of it increasingly runs on computation. And computation increasingly runs through a narrow set of tools. The lesson here isn't that ASML is too powerful. It's that modern systems reward specialization so extreme that power naturally concentrates. Efficiency creates fragility. Optimization creates dependency. And dependency creates risk. For decades, the global economy was built on the assumption that interdependence would create stability. That countries tied together by trade wouldn't risk breaking the system. ASML challenges that assumption. Not because it wants to, but because it reveals how asymmetric the system has become. When one link matters more than all others, cooperation turns into leverage. And leverage turns into pressure. The real danger isn't that ASML will abuse its position. The danger is that the world has quietly built a future that depends on perfection. Perfect machines, perfect coordination, perfect politics, and perfection is fragile. One miscalculation, one disruption, one escalation.